right. Hi guys. Good morning. Last minute check that you're in the right room. We're going to talk about Java here. If you forgot to switch the room after JavaScript, so it's less time. All right. So we're going to talk today about Java util streams. So if you have very strong desire during the talk to tweet about this, there's nothing I can do to prevent you from doing this, but use right hashtag JFocus. If you want to take the pictures of the slides, it's also good, but just take a picture of this slide because this slide is most important. It contains link to all materials that I'm going to be presenting today, the slides, codes, and potentially video. All right. Just a brief slide about myself. I work as a solutions architect with a company called Hazelcast. Hazelcast, how many of you guys heard about Hazelcast? Okay, so let's skip it. I work as developer advocate with Hazelcast, and I'm also in internet and tweeting about different stuff. And so this kind of interesting point that I realized today that I'm in Sweden, and this guy, Dolph Lundgren, he's also from Sweden, and he actually has, this is the guy who has one of the highest IQ among all the Hollywood actors. So because he has a master's degree in chemical engineering, and in this picture he also plays Russian. I'm Russian, so we kind of related, right? He's from Sweden, I'm today in Sweden, so I thought it would be appropriate. So yeah, now you need to go to follow me because I'm a very interesting person. Okay, now about agenda. I realized that usually people remember three things, so I'm usually trying to structure my presentation into three parts. So the first part, I'm going to do very brief, very short refreshing of the Java streams, and because it's important. We're going to talk about distributed data and distributed streams, and we look a little bit under the hood and how we did this in this presentation and in this project. All right, so when I talk to some people from big data world, they usually say, okay, in the big data world, like in programming world, you have a hello world. Like if you know how to write a hello world in programming language, you can put it in your resume. When you know how to do word count in the big data, using big data framework, you can put this framework in your resume. So today we're going to talk about a word count example, and there's the premise of this example. Want to keep it simple, so this is why we're going to use just one data structure, which is map. This map will be contain all our text files, which line the key of the map will represent number of the line, and the value would be line. After that, we need to find out how many times the particular word occurred in this text. So what needs to be done? Easy, right? We need to iterate through. We need to split these lines into words. Potentially, we can remove some of the non-words, remove some garbage. And that's it. After that, we can update number of total number of words. So very, very, very intuitive and naive implementation. So I loaded War and Peace, pretty big book, and I think I can consider this big book as a big data. And I want to read I want to make very naive assumptions about the content of the book. So if there is some word exists in this book for various stuff. I can see this word in this book like many times, so I can make assumption about, I don't know, like heroes, the main characters, etc. So we'll see how it goes. So first of all, like we need to read from the map. We're reading from the map. We do split by words, and after that we do this. How many of you use the map.compute already in production? Okay, cool. The compute method was added in Java 8, by the way, and in maybe from the very beginning, when I start talking about this technology, about distributed streams, I use this example which doesn't use Java 8. So you imagine you need to do map.get, get value. After that, you need to append this value. So it's too much code. With map.compute, you can do this in one line basically. So compute will accept the lambda. That by function that will provide the way how the mapping would work for particular key and for particular value, how the value will be computed if this value already exists in this map. So in this case, I have a key which represents my word, and a value, it's how many times this word actually appeared in the map. So next time when I see the same word, I'll just simply increase in the count. It's pretty neat, pretty convenient syntax, but there's many problems with this, and many of you already maybe know these problems. For example, this syntax allows us explicitly to iterate, so there is no clear way how we can parallelize this operation. So this is why we will refactor this code into Java 8 streams. Okay, so we're going to talk about how to move this code into the Java 8 streams, and after that we can operate this code into various situations. So Java 8 streams, first of all, it is a new abstraction that arrived in the Java 8 that represents a sequence of elements. That's it. It is not a data structure. It is not a new data type, or it's new data type, but it's just a way how you represent particular the pipeline that you're applying on top of the data. And the important thing is that streams they're not modifying the source of the data. So streams also like one off. And once you produce a stream and you execute a terminal operation, I'm gonna talk about this terminal operation a little bit. Then you're done. You cannot reuse this string. So why you should care? How many you using Scala? Okay, not many of you are going to be offended. The next slide. So the way how the Java developer think about Scala, first of all, it's ASCII art, some Chinese hieroglyphs, and some fancy things for the functional programming. Okay, it's not the regular one, the advanced Java developer, right? Usually the advanced Java developers, they're looking for something like the how to improve their code, like readability, how to improve code, the maintainability, etc. So, and you will be surprised, but many Java developers really do know Java. So this is why this API is important for them. And streams, it's about the Java, about data processing, how we process collections, how we do different transformations. So three types of operation available in the stream API. So intermediate operation or lazy operations that will not start the data processing. These operations will only define the procedure. And the terminal operation that will actually start the processing, operations like a collect or operation like a reduce, they will actually execute all this pipeline. But there's another type called, they call it stateful intermediate, or blocking, you can call it as well. Then these operations will not start executing this stream, but will block operation because, for example, sorted, it needs to go through the stream for each element of stream and apply the comparator to have sorted stream. And usually I like to think about the stream and the different stream operations same way as you prepare burgers, right? So you have a bun, and you start putting different layers of meat, tomatoes, lettuce, cheese, another meat, another cheese, another meat. And only after you're putting the bun on the top, this thing can be called a burger. So when you're putting your bun, it's your terminal operations. Intermediate operations, it's all your toppings, like your lettuce, your tomatoes, your pickles, etc. And let's see how we can refactor the previous code in a form of a streaming API, right? So you remember from the You remember from the previous example, what I had is I need to iterate over map. I need to do some of the intermediate steps. So basically, we will do source. We need to iterate over entry set because the map itself, as you know, it doesn't extend or doesn't implement the collection interface, and we know that stream method arrived in the collection interface. So now we need to get the entry set to get access to the stream, and after that, we will have stream that represents entry set in this map. As you remember, we have a key that represents line number, and we have a value that represents sentence. So we need to parse it. And in a Java Stream API, there is a very convenient method that can produce you another stream. So instead of producing stream of streams, you can produce like stream that contains new elements. So in this case, we can use a flat map. So flat map will take the parameter, and we need to produce another stream from it. I have the pattern string that represents the regular expression that will check if this particular, the token that comes from this sentence is a word. So I'll do split, and for particular m, which represents entry set, I need to get the value. Now, for the next operation, for the next step of this call, we now have a stream of words. So we don't have anything, we don't have lines, we don't have sentences, we just have words, which is cool stuff. Now we can do a different transformation. So for example, I can clean up some of the words. If the words contains some of the characters, I want to remove these characters. If the different pieces of the code contain, or different pieces of this text contain different words in different cases, I also want to remove this as well. So in this case, I will do, I have a special class that has method clean word. So what it does, it simply replaces non-letters in my stream. And after that, I can do things like uppercase or lowercase, if you prefer. String to lower. The next thing. Also, it maybe makes sense to me not use some of the smaller than 5 characters words. So in this case, I can use a filter, which will take the predicate, which is a function that returns true or false. So in this case, I need to provide a result, say word length, and equals around 5. Now I have my words. Now I need to start counting, and so this is basically a terminal operation that will take the stream that will contain some of these like very nice formatted words, and I will produce another map. And the Java 8 ships with very nice methods that can be used to collect data. So for example, this stream will be transferred into the map where I have a word as my key. And so the next thing, remember when we did compute, we also started with 1. So we see the word, we will put the 1. We see word another one, we put another one. So in this case, it's going to be 2. So in this case, it's count 1. And with the collect method, I also need to define the mapping function for key. So I have a left and right element that I need to just simply sum. Another option here is to use something like integer sum, which is also will be casted as by function, basically. Now, and I need to provide a result. You see, IntelliJ IDEA is smart enough. It says like I'm calling collect, but I'm never use a result. So in this case, count map will be my result, and as a result, I can see. Okay, now I remember I read this book in my childhood. I remember some of the main characters. So I remember a guy named he was a some royal person. His name was Andrew. So if I run it, we'll see that how many times Andrew existed. Okay, so the wrong one, wrong call. So I'll do Andrew, but not in this context. So I have accounts, do get. In this case, Andrew will be key, and I will see how many times I see Andrew. So with this example, like with this, like a 5 lines example, we're gonna work today. Also, I can apply different. Things here for my result. For example, I want to have a top 20. So in this case, I can use limit function. Also, I can provide sort this, so I can have a top 20. So I will be sort my streams with the comparator that will compare the value of the particular map, and after that I will write it down this like a top 20 words. And I guess this will be very simple. It's very simple use case to understand. Very simple use case to talk about. And top 20 Pierre, Prince, Andrew. Okay, so some of them, like I said, I remember some of the character was royal character. So see, we have a prince here. Now we saw some of the code. So let's talk about other problems that we might encounter in our real life. Okay, so when I'm running this on a laptop, like everything nice, and you're running it in a QA server, which is just one server, but sometimes you want to think, okay, so why I would need to have a cluster? Like my data fits perfectly fine, and sometimes your data doesn't fit perfectly fine, and you probably waited for this one, right? So when someone says simply, we expect Boromir to appear. So yeah, sometimes data, there's too much data that can fit in one computer, but in this particular case, I'm talking about map, then we're talking about memory. Maybe in some cases, the capacity of particular physical machine is not actually the problem. So for example, in our case, we're running Java, so our data stored in heap. So we know that we cannot do like really big heap until we have very good garbage collection that allows us to use like 45 gigabyte of heap or hundreds of gigabyte of heap. That would be nice, but still we need to work around this one. So one of the workarounds is to scale it, to store the data in another process or another machine. And sometimes that works because the data is too important to store it in one machine, right? So you need to have a backups. You need to have you need to store it in case of one data center might go down, and etc. So we understand the importance. How many of you heard about GitLab? And you understand the importance of backups, right? All right, I'm going to talk about the backups a little bit. Okay, so the first thing I want to talk about a little bit about the data distribution, like very short. So I have this picture where I have 2 examples of data distribution patterns. Who can tell me which is which? It's not fair. You knew this. Okay, so yeah, the gentleman over there looks like a professor. He knows this. So replication. So why I have terminators in replication? The thing is that replication is a pattern when you have a copy of the same data set that available on multiple machines. So essentially, it's the same copy of the one object, right? As a terminators, we have the same copy of the similar thing. Now, the second pattern is sharding. So we have one terminator, but sliced and stored different pieces of this terminator stores in different places. And the same way with your data is stored in different machines across the network. From the period of time for quite for a very long time, the sharding shows that it is more, not maybe convenient, but it's a right approach for scaling your data. Because with replications, you think you always limited with capacity of your smallest node in your cluster. So in this case, you need to scale up your data storage. And this is another example that shows like we developers more understand the square shapes and the round shapes than some of the, we understand some of the MEMS. So, but in many systems we can use replication and sharding as a combination, because in general it is more, it's more useful than just use one or another. For example, we have sharded data where we have one node has the keys from 1 to 100, and another node has values for keys from 100 to 200. Now, because we sharded this data, we created additional capacity on these nodes, because the one node doesn't need to store everything in one place. But with replication, you can store the backup that has data in another node. I'm going to show this in a couple seconds. Now, a couple other requirements that might arrive. During this conference, we talk about many speakers. They talk about different technologies and how they use this can be combined together. But there is always learning curve. You need to learn API. You need to know how to build this system, how to easy to use it. What's the API again? Is it possible to embed in the system, or it requires additional infrastructure? And can we run it in the cloud, etc.? So the thing is that one of the things that you guys already know this, you heard about Hazelcast, and the Hazelcast actually was there for quite some time for the reason of basically these 4 reasons, right? It is very simple. API is quite familiar for many Java developers, because Hazelcast provides distributed versions of Java collections. Hazelcast provides distributed versions of Java util concurrent package. So Java developers already know this API. And because the Hazelcast is just another library, they can drop it in the jar into the war application, or if it's the jar application, it's going to be in the class path, and Hazelcast will simply work. You don't need to use any additional infrastructure. Now, plus, with ability to discover other nodes using different cloud technologies, it makes it easy to deploy in the container, easy to deploy in the cloud like AWS, Azure, Google Cloud, etc. Now, and so we built another sort of extension on top of the Hazelcast, because if you think it would be quite natural to go from the collections to the streams, because the whole idea of streams is to provide bulk operations on top of collections. Now we have a distributed collections. Now we need to provide distributed bulk operations. So this is kind of some of the statistics about the Hazelcast. So far, we have over 1,000, or close to 2,000 stars. We have 134 contributors, including external contributors, people who not work for Hazelcast. So, and Hazelcast actually provides very simple approach for scalability. You have a commodity servers or commodity cloud machines, and with having this kind of commodity machine, they can create a very powerful cluster. If you remember from Matrix, the agent Smiths, they can create lots of troubles in Matrix. Plus, scale. Why it's so fast? Moving so fast. So this guy represents scale-up computing. So when you actually growing the hardware of the machines, in this case, it's going to be scale-out computing. But again, you can say, okay, Viktor, you just said that we cannot grow the JVM because it will be useless. So with Hazelcast, you can also use available native memory. So it's a heap plugin, but I'm not going to talk about this today, but it's possible. Now, again, the story about GitLab, you probably already read this from many sources. But my guy here also, like, not storing backups, but when he does, he stores it in memory. And this slides actually shows a thing that I explained a couple steps before. Then we can use sharding approach with a replication approach together that help us provide a resiliency in case of failure. So as you can see on this picture, I have a certain elements of my data that spread it across multiple nodes, plus there are copies of this data that stores in another node. So in case of failure of node 1, for example, the backup of orange data is stored on the node 2. So this data will be restored and will be provided for users. Now, do you guys want to see the demo? Because I saw many people raised their hands when we were talking about Hazelcast. Do you still want to see demo? Or, okay, all right, okay, cool. Yeah, I love it. So the simplest possible demo that where I can show this stuff, we can return to our example that we were working here. For now, we don't need this stuff. Just let me remove this, or as we do in our life, we're just commenting, we're never removing. Okay, so as I said earlier, that the API is very familiar for many Java developers. So what about just keeping everything as is, just changing the way how we instantiate this map? So in this case, I have a Hazelcast instance. 2 Hazelcast instances that will be running in this process. And instead of creating the hash map, I will request this instance from Hazelcast. And pretty much it, right? My method that will populate this data will stay as the same. And if I will run it, it will start Hazelcast as embedded node. It will start another node as another embedded node. They will join themselves into small embedded cluster, and we can see this cluster. Let me do a bigger screen to refresh. We can connect to this cluster. And I see two nodes, and my data that I loaded from the file like this. If I go here and do browse and do something like, I don't know, 5555, probably will not work because the key is integer. Yeah, there's some line of the text, which is what we expected basically. Now, when I talk about, okay, so we have this data in the cluster. Now, the resiliency, how does it work? As you can see here, from here, I have some entries that are stored in the one member. For example, you see 32K entries, and the same number stored as a backup in another node. So in a situation like, for example, like this, when I will shut down this node, the node will go down, but I will not lose my data. My 65K of text will be there. So as you can see, obviously I don't have any backups because I don't have any other node where to store it, but number of entries still there. And if I go to my browser, I can say, okay, can I request it once again? Okay, let's see what's next. Something is there. Okay, so now, without much of the change the code, just to change the way how you instantiate this map, we have data that basically might be stored in the cluster. Now we already have halfway there. Okay, now let's talk about distributed streams. okay, why we need to create this one? So why, for example, remember when I started this demo, I used the map, and from the map I used entry set, and from entry set I retrieved the set. So why this kind of stuff is not good in approach of distributed data when your data is in a cluster? Who have any ideas about why it is bad to run this kind of stuff? Anyone? Okay. How about this? So basically, as you might understand, then when you call the values or entry set, it will actually bring whole data to the client who invokes this. If you have data in the cluster, so what's the point to having data in the cluster? Well, you need to bring all this data into some node when you run this processing, right? So in this case, this approach, this will work. Like API-wise, this will work, but it will not be distributed computation. You will bring the data set into your client, and you do local computation of this data. This is not what we're looking for. What we're looking for is to have ability to send computation to the data. Because you already know from your career that every system that you work in, you have some storage, you need to bring data to do some computation and put it back. And sometimes data transfer is more time-consuming than actual processing, right? So in this case, having ability to send a tiny piece of computation next to the data, this is more important. All right. However, we have another problem, right? So the designers of Java Stream API and designers of the Java 8, they make this decision not make functions serializable, not make Lambda serializable. And one of the reasons that the Java serialization is not the nicest thing that we have in our life, and this is why we're looking for different frameworks that implements this more efficiently. Protobuf, Thrift, Avro, Cryo, name others. And the stream methods, they're not accepting any serializable version. So what to do with this? It's easy, right? We need to implement a serialized version of everything. So we need to implement a serialized version. We need to implement distributed stream. That will have all semantics of Java util streams, but have this condition that I named that we need to run computation into the cluster, not bring the data, but send computation. All right, so now I think it would be more exciting to see some demo, right? So with distributed streams, okay. So now this is word example that we already seen today that I wrote and I simply continue to use here. Now, some of the differences that you might see apart from the imports, this is why I hide all imports. I will talk about imports after. Now, you see my map now, which I retrieved from Hazelcast. I'll talk about this in a moment. So I retrieved this map from the Hazelcast, and now I can do map.stream. So in this case, the map that I stored in Hazelcast, distributed map, can implement stream. So it will give me a stream of entries. And after that, all these operations is absolutely same as you do with your local Java util stream. So, but you can say, okay, Viktor, what about the collect method, right? So it still sends data to map. But if you will be, if you see here, it's not just the Java map, though Java map also can be used. So in this case, it will send you that Java map. But it will store result in another IMAP, which is distributed map. So imagine you run the computation in the cluster, you crunch some numbers, and data is never left. Data will be created in place. So the result will be stored in place. There is no data movement. Everything is happen on the cluster. And to do this, let me show you how it would start. So in this case, I'm going to talk about a little bit of the new small project, not small, it's going to be big, project called Hazelcast Jet, which is built on top of Hazelcast. And to sort of emphasize that it built on top of Hazelcast, I have a Jet t-shirt on top of my Hazelcast t-shirt. So Jet is literally built on top of Hazelcast. Now, so to use all these the Java util streams, we need to create a Jet instance, which is essentially Hazelcast instance plus some nice sugar. So I will start my cluster that we already saw, and I load data there. It will start also like embedded cluster. I'll put some data there in some time. Now two nodes, loaded data. Data is there. Just let's see if data is there. Data is there. Come on, source. So we still have our data. Now, in my distributed stream, let's take a look on this piece of code. So in this case, my application that wants to execute distributed stream on the cluster, that will connect using Hazelcast client to this member. And the nice thing about the Hazelcast API, we don't have like distinguish between the member API and the client API. So in the different situation, if you invoke in different factor, it still will produce you a Hazelcast instance or Jet instance in this case, which depends what factory you invoked, will provide you a client factory of a client instance or a server instance. But API-wise, they'll be the same. So this will help, for example, you to start prototyping in embedded mode and ship your application in embedded mode. And after that, when you finally get funded to get new hardware for external in-memory cluster, then you can just simply change the topology without changing your code. So unified API, this is very cool stuff. Now I can execute this in my cluster. So what it will do, I will run this. So it connected and printed some of the results. So let's take a look on what it's actually created on my cluster node. So first of all, it created the map which contains counts. And as you can see, I have roughly 15K different words with different count numbers. I remember from my local version that the Andrew was kind of a big deal for this book. So let's see. Now we can use string, we can use Andrew, and we can browse here, and we have same number that we did with our local, or we can do Pierre, yeah. Yeah, this guy is even more important in this book. Now, another map that I created here is a map that will contain top 20, right? So in this case, I also have same thing that I did with local Java streams. That will provide the comparator, that will execute limit, and that will contain count, which contains only 20 elements. So if I'll go to my browser and I will do Andrew again, so I will see it there because he's in top 20. Now, any questions about this? Okay, so as you can see, the computation happened on the data that was stored in the cluster, and it created additional maps in the cluster which contains result. So it is pretty cool, I guess, I hope. So let me talk a little bit about what is JET and how it works. So we have a new website, jet.hazelcast.org, which contains documentation, architecture, and different useful readings for you. So Hazelcast Jet is designed as a general-purpose distributed data processing framework. The many existing big data systems, they have this notion of direct acyclic graph that defines the way how the data will flow inside the process engine. And the Hazelcast Jet implements this. We have this API that is low level, like a Jet API, that allows you constructing graph. So it's built on top of the Hazelcast. So Jet is doing only what is designed to do. So it is general purpose computational framework. All this low-level stuff, including connection, node discovery, and the different the data structure, cloud discovery, and all this stuff is handled by Hazelcast. I already showed my Hazelcast t-shirt underneath. And you can also say that it's comparable with Apache Spark and Apache Flink. I think more like a Flink because this is Jet designed to be a, even though it supports batching, batch processing, but it was designed to do streaming data processing. Some of the architecture of this one, as I already mentioned, that on top of it, it's Hazelcast. Jet provides native API, which is very expressive, I would say. However, to reduce this learning curve for many developers, we implemented Java util streams, first of all, to prove this idea that streams can be run in the cluster. Plus, the learning curve would be much slower. For example, if you're dealing with Spark, you need to learn Spark API. You're dealing with Flink, you need to deal with Flink API. Potentially, you can find some solutions like, for example, Apache Beam that tries to unify this processing, and they just have a runners like a Spark runner or Flink runner. But still, you need to know some of the internals. And with Jet, we think that you can start much faster with your project because you already know how to process this data using streams. And so the way how this DAG looks like, we have a source which contains the data, and we have the sink which contains data that will be pushed. And the vertexes will define different processing points, and the edges will represent the way how the data will flow from one place to another. DAG will be distributed and executed in all Hazelcast nodes. We're also handling the transferring of your artifacts, so your job will have some of the classes that you require. So these dependencies will be sent to executional nodes as well. Now the benchmarks. People love benchmarks. Who loves benchmarks? All right, cool. So the people usually asking like, okay, which is faster? They're not asking like, how long I need to learn, like what's the bottleneck, what's the cost, etc. So what's is faster? So the blue one is like, it's actually like the blue guy is actually destroying like a whole graph because you barely see how you can compare Jet versus other. But the blue guy is Hadoop. So we tested with Hadoop reference benchmark with word count. We have it on our website, the way how we tested it. And we're going to publish a source code of our benchmark as well. Now, I almost running out of time, and the couple slides. So the first of all, in terms of future, so it is a 0.3 release. It's pretty stable. You need to use it in production. It's a joke. But no, it is 0.3 release, and it's public. It's first public release that we work on this one for over a year and a half internally, and now it's on the GitHub, and you can go check the source code and play around with examples. So some of the things that we do in the next versions, we're going to implement different the processing guarantees, like a process only once guarantee, for example. We will adding more streaming features like the windowing or triggering. I already mentioned Apache Beam. Apache Beam is the project that plus SDK that was provided by Google, which they sort of design in Google Compute Cloud for the project Dataflow. And this actually, API unifies the way how you're dealing with streaming and batching data, like bounded and unbounded data. So we're also looking into this one to implement. Now, and support more data structure from Hazelcast, support different use cases, microservice use cases, CQRS, implement off-heap memory support for JET as well, so you will not run out of the memory when you're trying to produce some of the result in and your cluster doesn't have memory. Implement RX Java interface as another way how you can do the data processing, and add more connectors. So you can grab it from jet.hazelcast.org, source code in the Hazelcast repository. This is presentation and all materials. Instead of conclusion, Java Stream API, it's still quite powerful, and it creates good data processing. You can create different interesting data processing APIs. We have an example where we can compute something more sophisticated. For example, you can create TF-IDF index using Java util stream, which is also pretty cool. And War and Peace, it's really big, and in terms of data, really big book. And we know that pretty much Andrew and Pierre are the main characters because, you know, they appear in the book more often. Thank you for your time. Don't forget tweet. Don't forget to download the slides. And I will take some questions, because some of you want to go to grab some lunch or ask some questions right now. Any questions? Everything? So, yeah, please.
When do you schedule the release 1.0?
Say it again?
The 1.0 release, the production ready release.
1.0 release. Okay, I don't know. So what we're currently doing is in the Hazelcast release process, we're using a tool that allows us to run Hazelcast in a very, I would say, long time. So when we're running into, when we're releasing some of the new version of Hazelcast, we're running in a simulator for 24 hours or 48 hours. And JET will be integrated in this pipeline as well. And I can say that 0.3 it is already quite stable, even though, you know, it's a 0.3. But it is possible to use in production. Its API is pretty stable, and Hazelcast is rock solid, at least for 4 releases already since 3.4 when we start doing this. Hazelcast, the simulator runs every time. We now collecting you know, if some tests executed slower than previous one, regression. Yeah, I was trying to find, what's the word? Regression, yeah. And we're collecting this result. So I think it is already quite stable, even today. 0.1, maybe when we're gonna release Hazelcast 4, we're gonna release JET 0.1, because it's gonna be a huge change in terms of architecture, and after that, yeah. But I think maybe a year. And by the way, I do have some stickers here, if you stickers fan like I am. I have JET stickers, Hazelcast stickers. I know you know about Hazelcast, so grab the Hazelcast stickers. And if there is no questions, you can also ask these questions in my Twitter. This is why I put it there. Thank you for your time. Enjoy the rest of the conference. And Thank you once again.